So now that we've defined our binary encoding procedure, and we looked at some examples of how you can take these binary numbers and convert them into decimal numbers, in this lecture, we're going to kind of take the next step and we're going to look at some of the limitations of this system. And right, kind of the first obvious question to ask is, well, what's the biggest number, the biggest decimal number that I can encode using this method? Right, so to figure that out, first I'm going to let the sign bit be 0, because that's going to give us a positive number. Then for the exponent bit, now you might think we would want to put all ones here, right? But we can't do that. If you think back to the last lecture, a binary digit that has all ones in the exponent section is what's called a reserved number, right? That equals either infinity or not a number, depending on what the value of the significand of the f section here is. So I can't use the absolute biggest possible number, right? I'm going to go with the second biggest, which is all ones followed by a 0. So what does this equal? Well, if it had been all ones, it would have been 2 to the 11th minus 1. But this is 1 less than that, so this will be 2 to the 11th minus 2, which is 2046. So that's what I'm going to put in here to get my exponent. All right, and for the f value, here we can't just do all ones. Right? I'm going to put ones in here for everything, and that will give me my biggest possible significance. So what does that equal? Well, there's a couple different ways you could look at this. One is to say, look, this is 1/2 plus 1/2 squared plus 1/2 cubed plus down to 1/2 to the 52nd. Now, that is a geometric series. And there's a formula for the sum of a finite geometric series. And if you happen to have that formula handy, you can whip it out, put 1/2 in 1/2 in 52. That's going to come the answer. Now, I'll be honest with you, I do not happen to know that formula off the top of my head. And that's okay, because we can treat this just like we've done before with binary numbers. So I'm going to let this number, I'm going to call it f. And here's what I'm going to do. I'm going to add 0, 0, all zeros and a 1 to this. Now remember, this number here, this is 2 to the negative 52nd power. Right? If I add that number to f, what do I get? Well, in binary, right? 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1, so on, all the way down here, 0, 0, 0, 1. Right? So if I take my f and I add 2 to the negative 52nd power to it, I get 1. All right, so move that power of 2 over, and I get my answer. F is 1 minus 2 to the negative 52nd power. And if we put that in down here, we have to add another 1 to it. This becomes 2 minus 2 to the negative 52nd power. And that is my biggest possible number that I can get with this scheme. Now, if you can try doing that on your calculator, or you can go to one of the websites we talked about in the last lecture, where you can enter the binary expression, and it will tell you what the decimal value is. You get a number that is this approximately this, right? Obviously, I truncated the decimal points. If you really want to see all of them, you're welcome to go to those websites. You'll get the whole thing. The part I really care about here is this bit at the end. Right? Our maximum number is somewhere on the order of 10 to the 308th power. 1 followed by 308 zeros. So it's pretty big. Right? We can get some pretty decent sized numbers out of this scheme. Okay, so the next question, again, kind of next obvious question. Well, now that I know what the biggest value is, right? What's the smallest value I can get? And again, now I'm talking smallest in magnitude. Okay, so we're still thinking strictly about positive numbers, which is why I still have this S bit set to 0. Okay, now what are we going to do? Well, I want to minimize this expression here, right? So I'm going to run into the same problem here. Ideally, I would like to put all zeros into here, but again, I can't because referring back to that previous lecture again, a binary representation that has all zeros in the exponent part is a reserved number. That's either zero or it's one of those special subnormal numbers depending on the value of f. So again, I'm going to have to fudge this one a little. I'm going to put a 1 in there. Right, and isn't that okay? So fine. So c is equal to 1. If I put that in here, this is 2 to the 1 minus 1023. And then how about f? Well, there's no restrictions on f like there were on c. Yeah, so I'm going to put all zeros in here for f, and then this 1 plus f gets its minimum value, 1 plus 0. Given that f is always going to be a positive number, that's exactly what we would expect to get. So my result here is my smallest number is 2 to the negative 1022nd power. And again, if you go to one of these websites, that is approximately equal to that. Right? So there is our minimum possible number. Now, what happens, this is really going to be our topic in the next slide. What happens if you give it a number that is either greater than the maximum possible value or lower in magnitude than this minimum possible value? You get different results. If you give it a number that is smaller than this, the UFL, the underflow level, if you give it a number that is between that and 0, what most operating systems will do is they will round it to 0. Right? If you're adding and subtracting, yeah, it's so close to 0. Okay, that's kind of a reasonable thing to do. You do need to be aware if you're doing calculations and you're doing with really small numbers, and you suddenly start getting zeros for your answers where you didn't expect to get zeros, and you're doing any kind of multiplication. But obviously, if you multiply by 0, it's going to start turning all of your outputs into zeros. So that's kind of a red flag to keep in mind. And if you give it something that is bigger than the maximum possible number, that overflow level, most operating systems are just going to return an error. There's really no safe number that you can arbitrarily set that to. So you're going to get an error back. There are some special designed operating systems that are set up to handle that in some other kind of way, but the standard approach is just to return an error. So take a look at this number here, right? 1001, and I've got the binary encoding of that number on the right. This is exact. Right? This particular binary encoding gives us exactly 1001 when we decode its parts and put it into our formula. So 1001 is what's called a machine number. It's a number that can be encoded exactly using our procedure. Right? So what's the next number up from this using our binary system here? Well, to get the next highest number, I want to add the smallest possible value to our binary number. So that's going to mean taking this number here, this final digit, and turning it into a 1. If I do that, I get this, right, for my new number. And this is equal to 1001 point, whole bunch of zeros, and a 1. Okay, so how about if we go the other way? What's the next number down from this binary representation? Well, if I take this number and instead of adding 1, I subtract 1 from that last digit, we have to do a whole lot of borrowing, right, because of all those zeros, and we end up with this. And if you look really closely, this final 1 here became a 0, right, because I borrowed from that 1. It became a 0. Everybody else afterwards ended up being 1s. And the decimal representation of number is that number over here with all the 9s in its decimal place. So, what happens if I try to pass a computer a number between 1001 point all those zeros 1 and 1001? For example, what if I give it one of these numbers? Right? These numbers are exactly the halfway points. I averaged 1001 with the zeros and the one, and 1001, and I got this value, and I averaged 1001, 1000, and all these nines, and I got this value. What happens if we pass one of those numbers in? Computer's got to do something, right? Right? It can't just throw an error anytime I happen to hit a number that isn't a machine number, because there are lots of numbers that aren't machine numbers. So what does it do? Well, you've basically got two options. One is to truncate or chop the number, which basically means just dropping any decimal digits lower than our available precision. Essentially, that's equivalent to always rounding down. Or you can do kind of the more standard rounding that you learn back in elementary school, where if the very last digit is 5 or higher, you round up. Otherwise, you round down. So for that system, any digit that is between these two midpoints is going to get rounded to 1001. Any number that is outside of them either gets rounded up or rounded down, depending on which side it's on. Okay, so that approach to handling these kinds of in between, these non-machine numbers, may seem pretty straightforward. In an application, it I guess probably really is, but it does have some implications that we need to be aware of when we start trying to do arithmetic, particularly multiplication and division, with these non-machine numbers, and that's what we're going to look at in the next lecture.